Hello, well, I'm David Tappin, and for the BGS Open Day this year, I am going to present on tsunami hazard. And what I'm going to do is I'm going to give a brief introduction to that here. I've been in BGS a long time, and I've worked all over the world. I lived in the Pacific in Tonga for 5 years. And as a result of that, about 20 years ago, I became involved in researching tsunamis. Initially, it was on submarine landslides. There was a major event actually in the Southwest Pacific, but subsequently, all the major events which have taken place since about 1990. Indian Ocean, of course, and Japan, major events. And most recently, I've been working on the Indonesian tsunamis, 2018, Krakatau, a long way back, 1883, and most recently, the Tonga eruption of January 22, and I've got a few pictures of here. Spent a lot of my time digging holes in the ground and also spending a lot of time at sea, both metaphorically and physically. And on the right-hand side here, you can see me a long time ago when I was a lot younger, diving in Papua New Guinea. So what I want to do this afternoon today is really give you an introduction to tsunamis, the mechanism, all the different types of tsunamis, from earthquakes, submarine landslides, volcanoes, from the collapse and from eruption. And one of the things I'll be stressing is the importance of these recent events in better understanding events much older, where we didn't have the technology that we have now. And there's been major understandings during this time. Tsunamis have been a major hazard. Since 1992, there's something like about 250,000 people who have died in these events. I've got a little list here, goes back to Flores Island, Indonesia, in 1992. But the major events I've highlighted in red, and this is where there've been a major number of fatalities. 1998, Papua New Guinea, obviously the Indian Ocean, Japan, 2011, 18,000 people died here. And as I've said, recently in Indonesia, Anak Krakatau, and in January this year, Tonga. But this is a brief resume. In 30 minutes, I'm going to cover a lot of ground. And that first video I just showed you was from a film made in 2013, which actually was of the Indian Ocean Tsunami, based on a real life family who were involved in that and who survived. But it just shows you the tremendous power of the tsunamis. And so first I'm going to go to the definition. What are tsunamis? Well, tsunamis, it's a Japanese word. Fairly obviously, it means harbor wave. And I've got a little video here, and there's a whirlpool in this harbor, and the water entered the narrow entrance, and it created this amazing, spectacular phenomena, and hence the name, harbor and wave. And most tsunamis are recorded in Japan. If you go on Wikipedia, last 20, 30 years, you'll find about 50% of them are in this country. And there are three processes, and this process here I'm looking at is when the tsunami first strikes the land. But there's a source where the actual tsunami is generated. Then once that wave is generated, it travels through the ocean where it's quite benign. And the danger comes when the tsunami approaches the land and it rushes onto the land. There are a number of mechanisms. The most common are earthquakes, and which we understand reasonably well. The other mechanism, less so, but I will certainly be covering those. When we look at tsunami locations, as I've said, they're mainly earthquakes, and we find them all along the convergent margins of the world's ocean. Down here, we've got the Indian Ocean, up in the northwest in Japan, off of South America, but also close to home to the UK in the Mediterranean. There are tsunamis generated here. Two major events, which I'm going to deal with, are in the Indian Ocean in 2004, as I've mentioned, and then Japan, 2011. I thought I'd thrown a little bit about the UK because here we are, we're in this quite benign location up in the Northeast Atlantic, away from convergent margins. So our hazard is not that great, but it's not negligible. And I'll just briefly talk about that. The mechanisms, what happens? Well, what you need is a vertical movement of the seabed. And here along a convergent margin, you've got two plates converging. The lower one is dragging the overriding plate down. What happens? There's a rupture and the lower plate jumps up, upper plate jumps up. And what happens is because of that vertical movement of the seabed, it travels instantaneously through the water column. I'll move across here. And because water is incompressible, it creates like a step in the sea. Because of gravity, that step collapses and then that wave travels outwards. And here I've got it traveling down to the right-hand side. The wavelengths are very, very long. And the tsunamis, as most people know, travel really fast, 500, 600 kilometers an hour, the speed of a jet airliner. In the ocean, they're benign. You wouldn't notice them. Maybe about 50 centimeters, maybe a meter. But it's when the waves approach the land that the danger arises. Because of frictional on the bottom, what happens is the waves slow down and the wavelength decreases. And because of conservation of energy, the horizontal distance decreases, but the vertical distance or elevation increases. And that's when the danger comes. And these waves can be pretty high, 5, 10, 20 meters, often hundreds of meters. But if the earthquake is large enough, then that tsunami can be really quite hazardous. So what we have is you've got generation, the travel, the propagation, and then the on-land inundation. And I'm going to mention a few elevations here, but what I first thought would just tell you what these elevations mean. And here we have an 80-foot wave, 25 or 30 meters, and that's a human being. And if we come to Trafalgar Square in London, Nelson's column is 52 meters, and some of the tsunamis I'm talking about are 40 or 50 meters high. So just imagine Trafalgar Square being inundated by a tsunami. 52 meters sounds a lot, but the largest tsunamis, and there was one in 1958 in Alaska, it was over 500 meters. It's almost unbelievable, but we know that it actually happened. The first event I'm going to talk about is the Indian Ocean in 2004. Here we are, India and Southeast Asia and Sumatra. It was massively destructive. $15 billion worth of damage. But it was the fatalities around this ocean basin. Because of that tsunami, nearly 230,000 people died in all of these countries. There are about 4 or 5 main countries that were mainly affected. In Indonesia here, in the right-hand side, there are over 170,000 people died up in the north of Sumatra at Banda Aceh. In India, and there were something like 60,000 people, India and Sri Lanka. And in Thailand, there was something about 15,000. And if you look at the figure here, you can see that this is the travel time of the tsunami. And you can see in India, it takes 157 minutes, 2.5 hours. In Phuket, 111 minutes, 2 hours. So 2 hours after the earthquake, today we can warn people. You've got an earthquake here and a tsunami. There is plenty of time for warning an evacuation. But there was no warning system in the Indian Ocean. There was no evacuation, and all these people died. There was also actually evidence before the event that there were analogous events, but the take-home message from the Indian Ocean was that it really shouldn't have happened. One of the other 2 major aspects is that it resulted in a major review of earthquake tsunamis. They hadn't looked at tsunamis and earthquakes about 20 or 30 years. And so there was a major review, but also from tourists, we had, for the first time, lots and lots of pictures. And I'm showing you some pictures here on the right. And this is a lady in Thailand. She's a Swedish lady, and she sees her family in hazard, and she rushes out to save them. Amazingly, she survived. And because of this major European disaster, it had a huge impact on Western European American consciousness. And because of this raised awareness, people suddenly became very much aware. And the picture down here is that town on northern Sumatra, Banda Aceh. And you could see the damage and the devastation from the tsunami. 130,000 people died here. The result of the Indian Ocean tsunami was that whereas previously the Pacific Basin had a tsunami warning system, tsunami warning systems were erected in the Indian Ocean and the Mediterranean and the Caribbean. But after the Indian Ocean tsunami, once we'd better understood the mechanism and the impact, the question was asked, where would the next one happen next? The Indian Ocean, there hadn't been a previous event for decades. Well, the Indian Ocean wasn't well prepared for the tsunami, but the next one, with great surprise, 7 years later, struck Japan. Now, Japan up in the Northwest Pacific was the best prepared country on Earth for tsunami awareness and mitigation, but there were over 18,000 people who died. 300,000 people were made homeless, and the total cost of the event was 360 billion. And again, when I make a comparison with the Indian Ocean, there were a lot of fatalities and not a lot of damage, but in Japan it was huge. And actually, it's the costliest natural disaster, second only to Chernobyl in about 1985. There were lots of coastal farmlands destroyed, fishing boats destroyed. And you can see this is a tsunami wave rushing in over the tsunami wall. Up in the north of Japan, this town here, you can see the devastation. It's completely, utterly destroyed, and by a 40-meter tsunami. And just take your mind back to that image of Trafalgar Square. The major aspect of Japan, despite their preparedness, was they really didn't consider the earthquake magnitude that they experienced to be so large. And the result of that was the tsunami was far larger than they actually planned for. And again, similarly with the Indian Ocean, could things have been done better? There was another event about 1,400 years ago, but they also had the Indian Ocean in 2004. So what we're looking at here in Japan is similar event to the Indian Ocean. Not so many people died, fortunately, but a huge impact. And here's Japan, here's the earthquake, and these are the elevations of the tsunami. Tokyo's down here somewhere. And that tsunami in Minami Sanriku was 40 minutes. The difference between Japan and the Indian Ocean was that Japan faces the massive Pacific Ocean. So major damage was actually on Japan, in Japan, not affecting many other countries. So there were major events, but the impacts were different. But there was a lot of lessons that we learned from both events. We know that these earthquakes can strike along any convergent margin as long as it's large enough, and all the ocean basins needed a warning system, which after Indian Ocean, they actually had. In Japan, they considered the Indian Ocean, but they really didn't take some of the major lessons. The earthquake, as I've said, was massive 9, but and this was 30 times larger than the earthquake they anticipated. One of the major aspects of Japan was Fukushima, and I've got a little video there, but it doesn't seem to be working. I've mentioned tsunamis from earthquakes, but they're not the only mechanisms, and the mechanisms I'm going to talk about now, are ones that really wasn't considered before about 2000. And they're submarine landslides and they're volcanoes. And I've got a global map here. And I've got all the plate boundaries here and the passive margins. And in red, what I've got are the locations where we have submarine landslide tsunamis. And they're up here in the northeastern Pacific, Alaska, the Aleutians, in the Mediterranean here, and they're near Italy, in the northern Indian Ocean, over in Japan, and in Indonesia. And for volcanoes, what I've got in white, they're associated with tsunamis, Hawaii here in the Central Pacific, the Canary Islands, quite close to us in Britain, Santorini in the Aegean, volcanoes in Japan, and of course the major volcanoes between Sumatra and Java, Krakatau and Anak Krakatau. And less well known in Papua New Guinea is Ritter Island. But just to come back to submarine landslides, I've already mentioned the UK and we don't have that much of a hazard. There actually are a couple of pretty serious landslide tsunamis off of Canada, the Grand Banks, and also Storega, and I'll be mentioning those in a little bit of detail. But these events, Storega and Grand Banks, are quite old. And Grand Banks is 1929. It's well known because the cables on the seafloor off of Newfoundland one day in 1929 were broken. And we know they were broken because people in America and England were talking to each other, and suddenly they were cut off. And they probably got onto the GPO and told them, you know, ask them what is going on. But what was discovered subsequently was that there was an earthquake and a tsunami, and 27 people died in the tsunami, which was 5 meters high, which, if you consider relative to those previous events in Japan and Indian Ocean, it's not very much. I would say there's not much of a UK impact because the earthquake was quite small. And because it was quite small, there was some consideration about could it have caused a tsunami. But from the cable breaks, it was interpreted that there was a landslide, and the landslide was only interpreted from the breaks because the event predated how we map the seabed. And as I've introduced at the beginning, it's technology that have allowed us to understand not just earthquakes, but also these non-seismic, non-earthquakes events, such as submarine landslides. The other major event, which was a submarine landslide, is off of Norway. Here's the UK, here's Scotland, here's the Shetland Islands. And 8,200 years ago, it's prehistoric, there was a massive landslide. It's about as big as Scotland. And there were the tsunami elevations, the run-up, were 20 meters on the Shetlands and also 3 to 6 meters on the east coast of Scotland. I don't really have time to go into so much detail, but obviously 8,200 years ago, there weren't people who were writing down records, or there weren't scientists like me who are doing the research. But when the tsunamis flood the land, they lay down sediments. And on the Shetlands and on the east coast of Scotland, these sediments were discovered. They were dated as the same age as Storega. And from that information and a leap of scientific interpretation, it was recognized that this big landslide had created this huge tsunami. And of course, in the North Atlantic, there's not really an operative warning system because nobody really considered this tsunamis a major hazard here. Obviously, Storega, there are no recorded casualties. And as I've sort of stressed at the beginning, a lot of the research is based upon the fatalities, but Storega was researched because there's a massive gas field. Ormond Langer understand it. It provides a lot of the UK gas, but because they were concerned that if they took the gas out, it would trigger another landslide, which could inundate Norway, but also the UK. They spent a huge amount of money researching it. The big event for submarine landslides was Papua New Guinea. Papua New Guinea here is north of Australia. And in 1998, there was a massive tsunami, 15 meters high, which inundated this idyllic lagoon on the north coast. And there was a sort of images of damage. This was a house which was completely destroyed. The tsunami was up to 15 meters high. You can see this is the coastline, which was inundated, and this is the tsunami. You can see it's up to 15 meters in this area. The problem was that the earthquake was small, magnitude 7. And we don't expect that to trigger a tsunami. It's similar to the Grand Banks event. The other aspect is the earthquake was over here, but the major tsunami was here. So it was this disconnect. In addition, there was a 20-minute delay between the earthquake and the tsunami. And if you had an earthquake here, then the tsunami would flood the land almost instantaneously. And the result of Papua New Guinea was it actually recognized, in spite of Storega and the Grand Banks, that seabed sediment movement and slumping could be really hazardous, and most importantly, it could kill people. Papua New Guinea, apart from the devastation, is also important because it led to 5 major offshore expeditions. Part of those, some of which I led, we mapped the seabed off of the inundated area. And this is the seabed here. For some of you, it's a convergent margin, it's a deep trench. And from the seabed morphology, we identified a slump. And I've just thrown in Wales here, 19,000 square kilometers mapped in 14 days. And that's pretty much the area of Wales. So just imagine mapping Wales in 14 days. It'll be quite a challenge. But from the interpretation of the seabed morphology, we identified a seabed slump. And as I said, I was involved in these. And one of the aspects of that is diving down to the seabed. And here we are at 1,600 meters, and I'm in a submersible. You can see this octopus, and you can see all these blocks. And these are blocks of limestone, which have moved as that slump moved. And he's actually eating, there's all sorts of the mussels down here. So it's a bit like McDonald's, he's going for his takeaway. And you can see the fractures in the limestone as they have traveled down the seabed as part of this slump. For the first time, because as I've said, like understanding tsunamis from non-seismic sources is difficult, and modeling them even more. This was the first time that we actually numerically modeled a tsunami. The slump was here, and you can see the tsunami waves traveling southwards and inundating that idyllic lagoon. How do we know that the numerical models are accurate? Because actually scientists went in and they mapped the inundation and the height of the inundation on the coastline. And what you see down here on the bottom are the measurements of the tsunami from the on-land observation, and that's the actual modeling. And you can see that this slump here, when it failed, generated this tsunami. And this is one of the first times in the modern era, the modern time, that we actually demonstrated that a slump can cause a tsunami. And I've got a little cartoon up here. This is the slump beforehand. It moves down the seabed. It's a bit like an earthquake. And what it does is it changes the height, the elevation of the ocean. And the tsunami travels out oceanward. But of course, the major impact was closer to shore. This was the first time that a marine survey had taken place. And it was the first time we'd actually used this new mapping technology, which I outlined earlier, but also the first time that we really had a detailed numerical model of the tsunami. And at that time in 2000, it's 20 years ago now, it was very controversial. But what it did do, it made people reconsider older events. And some of those were Storega in Europe, and obviously the Grand Banks off of Canada. So I've dealt with earthquakes and I've dealt with submarine landslides. But next, I'm going to deal with volcanic tsunamis and their mechanisms. Now, volcanic tsunamis are even more complicated than landslides, because when a volcano erupts, there are all sorts of different mechanisms. You can have an explosion. The actual caldera in the volcano can collapse. You can have a huge eruption column, which on collapsing could also fall into the ocean and trigger a tsunami. You could have a massive explosion here, lateral blast, but also when hot magma acts with cold seawater, you can have a massive explosion, and the explosion can also send out shock waves. And there aren't very many eruption tsunamis, but there are quite a few, and I've got identified a few here. Out in the Pacific, there's Hawaii, that's a submarine landslide, the Canary Islands, again, closer to home, eruptions in the Mediterranean, in the Aegean, Santorini, over in Indonesia, Krakatau and Anak Krakatau, Ritter Island I've mentioned, but also most recently Tonga in the Western Pacific. But what I'm going to talk about now, these two recent events in Indonesia, Anak Krakatau in 2018 and Tonga in 2022. Krakatau is the big one. I'll mention this. Here it is between Sumatra and Java. Huge eruption. I've got an image of it here. The volcano was completely destroyed, and the tsunami on the coastline, you can see, was up to about 30 odd meters, 36 meters here on Java. 36,000 people died, and it had a global effect. And this is a picture of the Scream by the Norwegian painter Edvard Munch. And one of the aspects of the tsunami was it pumped up all this ash into the mesosphere, stratosphere, and it caused all these amazing red sunlight. And you can see this was the basis of Edvard Munch's painting. It created a massive shock wave that went around the globe, and it also caused a local tsunami. And here I've got a little image. This is from a publication by a Dutchman called Verbeek, and he mapped the inundation of the tsunami. And it was the first field survey that was ever carried out, and his work is important because of the work now we're doing in Anak Krakatau. We can come back and we can compare his work at the time of the eruption to the work we're doing about 40 years later. And the other importance of Krakatau is that there are 42 active Krakatau volcano-type volcanoes on the planet. So to understand what happens in Krakatau could help us mitigate against eruptions and tsunamis from these other 41 events. In Hawaii, I've mentioned, it's another location. Hawaiians in the middle of the Pacific. Here's the big island, the small islands trailing off to the northwest. And offshore, there's a whole series of slumps and debris avalanches. And these slumps and avalanches are really absolutely enormous. And I'm going to show you a picture here of the Nuanu. And this is something like about I've got 1,000 cubic kilometers, but that's an underestimate. This is about 2,000 cubic kilometers. And some of the blocks here, and this is the Tuscaloosa seamount, that's over 1 kilometer high. It sits on the seabed. And you can see the blocks, which are distributed to the north of the main islands of Oahu and Molokai. Fortunately, we don't know there's any historic events, but we do know that they're probably related to climate change. And we do know that the tsunamis are over hundreds of meters above sea level. On the right-hand side here, this is a model of a tsunami from the Alika slide. And the Alika slide is about 120,000 years old. And our numerical models show that the tsunami here was 800 meters above sea level. I've mentioned Lituya Bay, but you can see that close to land, these collapses are definitely very, very hazardous. As I've said, fortunately, they're not historic. And in Honolulu, the main town, and in Hawaii, the main town of Honolulu is here. And you can imagine this happened today, Honolulu would have been completely devastated. Two recent events now. Anak Krakatau, again, between Java and Sumatra. In 2018, it collapsed. There was a major collapse of its flank. And the collapse was associated with an eruption that had been going on for about 6 months. But the tsunami on the adjacent coastlines killed over 400 people. Numerous people were injured, and there were obviously a lot of people, a lot of houses destroyed. From satellite imagery, we know that this is the volcano beforehand, that there was a southwest flank collapse. So it collapsed in this direction, and here's some seabed bathymetry. This is the island, and this is this very deep basin. And these are these slump blocks which formed the collapse from the islands. These are angular slide blocks. There was this, the volcano was erupting. There was a quite vigorous event, and they blocked and they failed down the slope. And you can see these are huge blocks, and you can see almost the shape of the slope of the island. They are quite coherent. Okay, now what we've been doing here, we've been numerically modeling these, and I hope this is going to work. But this is the numerical model of that slump. Here are the surrounding islands. This is Krakatau, and the slump failed in this southwest direction. And this is the tsunami which was generated. And you can see the slump, the sediment collapsing and traveling outwards, a tsunami wave traveling outwards. And on the surrounding islands, Krakatau, the tsunami was 80 meters high, 80 meters. So go back and think about Trafalgar Square. But in the farther away, what we call the far field, you can see the tsunami traveling away and striking the coast of Java here in the east and Sumatra in the north. Okay. So why and how? Well, we know that the volcano grew up in this big hole created when Krakatoa erupted in 1883. And one of the reasons for the major instability was that the volcano had grown up since 1883 on the edge of this very deep basin, 220, 250 meters deep. And that had created a real instability, which when the eruption took place, triggered the collapse into that deep water basin and the tsunami. Even more recently than 2018, earlier this year, January the 15th, there was a massive eruption off of Tonga. Tonga here is in the Southwest Pacific. Here we are, is Australia, Papua New Guinea, New Zealand. Here's the island. It's an underwater volcano. It's been very, very active over the past 20 or 30 years. And it was not a major surprise. Anak Krakatau was a surprise. The Indian Ocean was a surprise. Japan was a surprise. Fortunately, there were few fatalities, but there were tsunamis locally on the coast of the adjacent Tongan Islands. And there was a massive explosion, one of the largest explosions ever recorded, which actually destroyed the island. You can see the island here. That was gone after that explosion. But there were also far-field tsunamis that traveled across the Pacific Ocean. Compared to Krakatoa, fortunately, the fatalities are very low, but Tonga is very important because actually there are a lot of similarities with Krakatoa itself. And the tsunamis probably were from a collapse of this huge explosion, the ash plume, maybe as water entered the caldera, or even perhaps from caldera collapse. And as I've said, it's an important event because it's the first one we've had since Krakatoa that will provide modern information on how Krakatoa tsunami was generated. Here's some satellite images here. Here's the volcano before, and here's the volcano afterwards. Completely destroyed. This is this massive explosion, and this went up into the mesosphere, 58 kilometers. It was huge. How big is that? Well, I've got a little similarity here. This is France. I'm sure you will recognize that, and that's the explosion. So just imagine if something like this happened on the Massif Central. There's been a lot of work done by my New Zealand colleagues. They've been mapping the seabed. You can see here, this is the volcano. The sea level is about here. And this is a very close up of that caldera. And the caldera before the eruption was 150 meters, and afterwards it was 850 meters. And that was all because of this massive explosion. When we look at the far field tsunami, you can see this is Tonga. It travels all the way across the Pacific Ocean. And we know that that actually was due to a massive shock wave that traveled 3 times around the globe, but it drove that wave all the way across 15,000 kilometers across the Pacific. The local tsunami flooded the nearby coast of the main town of Tonga Tapu. This is a little blow up here, and you can see this brown area. This is very low lying. It's less than 15 meters, and sorry about that. And the pale brown area is where the tsunami struck and destroyed a lot of the results there. And this is this eruption column. It's a picture taken by local scientists. And I said that went up something like about 58 kilometers. There are different mechanisms, and we're still working on it. In the far field, as I've said, it was probably the shock wave that traveled around. But in the near field, and we're still working on this, it's likely that, is that going to work? Yeah. That it probably was cold water entering the magma chamber and exploding. But we're having a lot of discussion about, some of my colleagues think that big plume collapsed and that generated a tsunami. But as far as Krakatau is concerned, it will give us a lot greater insight into the mechanisms there. But as I've said, we're still working on that. Why study tsunamis? Well, it's great fun. Apart from the death and destruction, and the fatalities, I mean, we really are learning so much, and that information is feeding into mitigation. But I thought I would throw this slide in, but people in Britain say, why do we study tsunamis? You know, is there a hazard? Well, there is. And I've got a little map here. I've mentioned the Grand Banks and Sterega. And it's a big landslide there, which flooded the coast of Scotland. There was an earthquake, Lisbon, 1755. It destroyed Lisbon. There was a small tsunami, and there are the Canary Islands. And the Canary Islands are volcanoes. They're similar to Indonesian volcanoes and to Krakatau. In the Canary Islands, the last big event was 13,000, but some of you may have followed the press at the end of last year, and on La Palma, which is very much a popular tourist resort, it erupted and it covered a lot of the island in ash. And we do know from the Canary Islands that the eruptions do trigger these giant landslides similar to those of Hawaii. A little bit closer, in the Dover Strait in 1580, the chalk cliffs collapsed. But all this is a separate talk on its own. Also, as Greenland ice melts, is it possible that there could be landslides off of the East Coast? We don't know. That's a bit fantastical. But the challenge here is, because they're low frequency, our impact, how we actually address them. But we're working on that. So, considerations and why study tsunamis? Well, it's interesting, fantastic science. There are varied tsunami sources, and from what I've told you, some of the individual events are devastating. And as the Indian Ocean shows, and what I'm talking about, the Canary Islands, and also I mentioned Santorini, whereas previously these events happened to other people, far distant places with global travel, and Indonesia it is a case in event. Suddenly, you know, local English people, Scottish people, Welsh, Europeans could be in a situation where they are in hazard. They're mainly earthquakes, ubiquitous in subduction zones. And based on the Indian Ocean and Japan, we know a lot more. Numerous landslide mechanisms, submarine landslides, Submarine, I haven't mentioned those, not very many. The volcanoes, landslides, eruptions, explosions, and shockwave, really very, very complicated. And the Tonga event is really throwing a lot of light on that. Convergent margins, obviously, the major hazard zone, but passive margins too, the North Atlantic. The landslide tsunamis are harder to model for a lot of different reasons, but basically it's velocities, earthquake rupture at kilometers a second, and landslides travel much slower. The magnitude depends on the source and the scale, huge earthquakes, smaller landslides perhaps. But the triggering, why we study them, is because of the realization that they are hazardous and they can cause huge fatalities and also major impact. Japan, what did I say? $350 billion worth of damage. And a lot of our advantage advances are not just based on the fatalities, but the new technology that we have in mapping the seabed, numerical models, computers, GPS, the way we can locate ourselves. Now, a lot of the older events, for example, Krakatau I've mentioned, that technology was not available. But the main thing is, and this is one of my main motivations, is we can feed it into mitigation strategies that in the future, hopefully, could save people's lives. Thank you.